Hi folks, Mr. Long here. We're going to go ahead and get going again and do some more work. We're going to come up with an equation of a tangent to, part E here, equation of a tangent to f at x, okay, to f at x equals 0. And so there's, again, some things that we need to think about. Okay, what's the relationship between f at x and this graph, g of x? Always, always, always. Let's write those down. So I know that f equals the integral of g from 5 to x. Again, that's not the best notation. You wouldn't put that down on your exam, but that gives you the overview of what you are doing. But if I differentiate both sides, if I differentiate f, I get f prime. If I differentiate an integral, it just gets rid of the integral. I'm left with g. So that's just g. Okay, so that's going to be useful. Oh, by the way, you may see, it's not very often they do it in the AP exam, but sometimes they'll call a tangent a linearization, which makes perfect sense, right? Because all a tangent does is it linearizes a curve in the vicinity of a point. Okay, so if you see a linearization, and they might call it L of x, linearization, and depending on x, it just means a tangent. Okay, it just means a tangent. Let's take a look at this question. So what do I need to do? Well, we know the general formula for a tangent is that, and I'm actually going to call it L of x, linearization of x, tangent. F prime at a, it's in terms of f here, so I'm going to write it f prime at a, x minus a plus f at a. Okay, I'm going to write it that way. And sorry, I'm just drinking my tea as well as doing this. So I need to do that. So I need to get f prime at a. First of all, what is a? I'm pretty sure in this case that a is, for this problem, a is equal to 0, right? A is equal to 0. Okay, a is equal to 0. So what I need to do then is I need to get f prime at a, I need to get f at a. So how am I going to do that? Let's take a look. So let's see. So what is f prime at a? Let's do that first. So I'm up in the top left here. F prime at a is the same thing as f prime is 0 because a is 0. But what's f prime? That's g. I have to take every bit of information that I need to know about f, and because I'm going to extract that off the graph of g. Right? The graph of g is what I have to work with. So I've got to relate those graphs. So I've got to get g at 0. Well, what's g at 0? So x equals 0, go up and read the y value. It's 4. Okay, so I know that f prime at a is 4 because g at 0 is 4. Okay, next thing. I have to find f at a. What's the y value? Well, f at a is just going to be f at 0. What's the relationship? It's right there. Okay, the relationship is there for f. For f prime, I read g. For f, I have to integrate g. So it's going to be the integral from 5 to 0 g of t dt. I don't ever write integrals with a lower number on the bottom than the top. Or sorry, a higher number in the bottom, a greater number in the bottom of the top. So I've got to redo it and put the negative sign out front, and it's going to be the negative of 0 to 5. So now, when I do 0 to 5, I can just simply start at 0 here. Start at 0 there, and then start reading to the right. So the first area I encounter is positive 8. The second area on my way to 5 is 4.8, but it's negative because it's below. And then that takes me to 5. Okay, so there's two areas between 0 and 5. So it's the negative of 8 minus 4.8. And then that's going to work out to negative 3.2. Okay, 8 minus 4.8 is 3.2. Take the negative of it, and it's negative 3.2. So that's our f at a value. Now we can just go through and substitute in our values. So the tangent slope we know is 4. And our a value is 0. And our f at a value is negative 3.2. So then I expand through the brackets, gets rid of the 0, so it's 4x minus 3.2, and that's our tangent. Okay, folks? So again, the big idea there is you need to use these two relationships. F is the integral of g, f prime is g. Okay, now we're going to get the tangent to g of x at x equals 3. So here's another question. So first thing you ask, is this question just about g, or do I have to relate it to f? Well, no, I just have to work with g in this case. So I need to get a tangent to g at x equals 3. What equation will I use? Well, I'm not going to use f anymore. I'm working with g. So it's g prime of a, x minus a, plus g of a. G prime of a is the slope of the curve. So I need to go to x equals 3, right? I need to go to x equals 3, and I need to get the slope there. Well, I've got a tangent right here, right? I've got a tangent. A tangent has been given. And if I look at that tangent, it has a slope of negative 8 over 1. Okay, negative 8 over 1. So when I do that, I know that that's f prime at a, or g prime at a rather, is negative 8. And I know that the a value is 3, right? The a value is 3. And g at a is, what's g at a? Well, what's the y value right there? It's 0. Okay, so negative 8, x minus 3 plus 0, expand through the brackets. Negative 8x plus 24 is our equation of the tangent there. Now, do I have to go further than this on the AP exam? No, you can just leave it like that if they're asking for a tangent. You don't have to expand it out into y equals mx plus b form. Now, by the way, over on this side, if you had x minus 0, I would expand through that because they're not going to want to see just a 0 there, I don't think. But if you've got a number here, you can just leave it like that and move on. Okay, so let's try another problem. Okay, this is a classic question that is often on. You're given a graph like this, and then it asks you for an absolute minimum or maximum. Okay, an absolute minimum or maximum on an interval. So let's think about that for a second. Absolute minimum or maximum. So if I had a graph like this, and this was my interval, and I had to find the absolute minimum. How do I do that? Well, I look at the y values at the endpoints, there, and then I look for any minimums. I've got a minimum there. So then what I do is, and remember, I'm showing you the graph here, but in fact, often you won't have the graph, because you don't have the graph of f, you only have the graph of g, and it does say the absolute minimum for f at x. So what I have to do is get the y value there, get the y value there, and then anywhere where I know I have a minimum, I have to get that y value. And so I check those three numbers, and the lowest one is going to win out and be the absolute minimum. Okay, so again, check the endpoints, check any minimums. So the easier thing to do, I think, in most cases, is just to get the y value of your endpoints, right? You want to just get the y value of your endpoints. So we're going to do that. So the first thing we're going to do is our endpoints occur at negative 1 and at 9. So if we do this, I believe we've already calculated the y values at negative 1 and at 9. So the first one, again, to define f at x, we are doing the integral from x equals 5 to whatever the x value is inside here. So we've done that. I think we got negative 8.2. But it's you know, we can count backwards and figure it out, right? So as I go, or actually count, well, it's 5 to negative 1, so it's going to be the negative of negative 1 to 5. So positive 5, remember it's positive 5 here, right? It's positive 5 here. That was a 5 there. So it's 5 in this area here. Then it was 8, that's 13. 13 minus 5 would be 8. So it's actually only 8.2. So the area left to right is 8.2. But since the original integral is 5 to negative 1, we have to reverse it. So it's negative 8.2, okay? Then we have to do the other endpoint. from 5 to 9. Now we have to do the area from 5 to 9. That's more straightforward because we're going left to right. So it's going to be negative 5.5 for that, minus that 1.8, plus 1.5. And if we add that up, so did you notice a mistake I made there? Look at that. Again, it's one of those tricks. That's 1.5 there, right? So if that's 1.5, we need to get the area of this part here, right? The area between the curve and the x-axis. That's the area above the curve. So that's 1, 2, 3, 4, 5. By 1, that's 5. So that makes that 3.5. Okay, so it's going to be negative 5.5 minus 1.8 plus 3.5, and that works out to negative 3.8. So we know the y value at the far left of f is negative 8.2. The y value at the far right of f is negative 3.8. So that what we're left with is there any local minimum? And when do you get a local minimum, right? When do you get a local minimum? Now, this is kind of hard to see here, so I'll just do this over here. There's a local minimum if the derivative function decreases, then it goes horizontal for an instant, then it is positive, right? We get a local minimum, or we call that a relative minimum or a local minimum. If it decreases, goes horizontal, and increases. Let's see if we can look at this graph and find that location. Remembering that this graph, folks, f prime, we're looking for when f prime equals 0, right? And we're looking for when, especially when f prime goes from negative to 0 to positive. What's f prime? F prime is g. So I have to look at the x-intercepts on the given graph. Okay, f prime is g. So let's look at this one. Is that a minimum or a maximum? Well, the y value on this curve, which is the slope of f, the slope goes positive, 0, and negative. That's a maximum. There's no change in slope. You know, it hits an intercept and turns back down. So that's not a max or a min. That's probably a saddle point. Then I go to this one here. Well, notice here that the y value on g is negative, which is the slope, that's f prime. So in this case, it does go down, it hits 0, and it turns and it goes back up. So it looks to me like we've got a minimum at x equals 8. Okay, there is a minimum, a local minimum at x equals 8. Is that a global minimum? Well, we have to find that out. Let's take a look and see if we can do that. Local min at x equals 8. So all we need to do now is to find the y value at x equals 8, do our integral. Okay, do our integral, which goes from always starting at 5 and it goes to 8. So what areas do I have? I'm starting right here at 5. I've got negative 5.5, minus 1.8, and that's it. That's the only area. That's negative 7.3. So now what I do is I compare my y values. What are my y values? My y values are negative 8.2 at negative 1, negative 3.8 at x equals 9, and negative 7.3 at x equals 8. Which one of those is the absolute lowest? The winner is x equals negative 1. That's the absolute lowest, negative 8.2. So there's an absolute minimum of negative 8.2 at x equals negative 1. Remember that when we talk about absolute minimum or maximum, we're referring to y values. Okay? So if you are asked for an absolute minimum, you state the y value. I would always state the x value as well. Now, the question could say, what's the x value of the absolute minimum or maximum? You could state that as well. But again, process-wise, always do the endpoints, and then if you're looking for an absolute minimum, find all the minimum values on the original curve. Okay, last slide for this one. So the first thing we're going to do is we want to find any intervals where the curve f at x is both increasing and concave down. This is easier than you think, and this is also a very, very common question. So look at this. So what does this mean? Well, if it's concave down, the second derivative is negative. That's F. But remember, we're working with G. So what is, and again, I would always do this. We've got this statement right on the curve, but I would always write F prime equals G and F double prime equals G prime. Okay? I would always do that. So we want to have G prime less than 0. So where is G prime less than 0? Well, I've got to find G prime less than 0 for concave down. So the slope has to be negative. So where's the slope negative? Well, there. All along there, it's still negative, right? The slope is still negative there. Slope is still negative there. Okay, that's fine. That's all negative slope. Okay, because again, the slope of this curve is the concavity of F. Then I've got that slope is negative there. That slope is negative there. And that's it for negative slopes. Okay, so that's done. I figured out where there's negative slopes. But it also says the function is increasing. F at x is increasing. So what does that mean? Well, if f at x is increasing, then f prime is greater than 0. But what is f prime? It's just g. So how do I read f prime from this graph? I just look at the y value. So where is the y value above 0? Well, the y value is above 0 all along there and that little part there. Okay, that's where the y value is 0. So I'm looking for where both of those are true. Well, look at this. We can see very clearly where's the only location where g prime is negative. So that means a negative slope on g, sloping down, it is. And where the y value on g is positive. Again, what does the y value on g measure? The y value on g measures the slope of f. Okay. So the interval is going to be from -1 all the way to 3. Okay, points of inflection. Where do points of inflection occur? Points of inflection occur when f double prime is 0. Okay, and if there's a change in sign. Okay, there's a change in sign in f double prime. So, and what is f double prime? F double prime is the slope of this curve. Okay, so there has to be a change in the sign of g prime. Well, what does that mean then? That's a change in the slope. Okay, the change in the slope. So where does the slope change on this curve? Well, let's see. There's a change in slope right there. 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 Okay, so I see 1, 2, 3, 4, 5. So remember that on the first derivative, because remember g of x is a first derivative of f, on the first derivative, anytime you hit a max or min, that means the slope is changing on the original function, right? Remember that those points of inflection are maximum levels or minimum levels of slope. So if we go through that, if the slope of g changes sign, then we have a POI, okay? Slope up on f, a POI on f. So where are our POIs? At 4, at 5, at 6. That little one there looks like it's about 6.5. And then the other one down here looks like it's about 6.7. Okay, those are all points of inflection. Okay, points of inflection. And again, it's that relationship right here that you need to work with. This is hard stuff. Okay, and so that's our last slide for this video, and then we've got, I believe, one more.